Okay, how about if he goes over
Now.
5 minutes?
Okay, 5 minutes.
Okay, here we go. I mean, I get full attention though.
Okay.
Okay, so here we go. So we're gonna look at a little optimization problem, right? So we've got this situation where we've got a sheet of cardboard, 9 inches by 5 inches, and we want to figure out how to create the box with maximum volume. Right now, we're going to cheat a little bit. We're going to set up a polynomial function and then use graphing technology to find the maximum. In calculus, we won't need the graphing technology part. So does everybody see this is what we're going to do? Right? So this is a useful picture, right? This is where we're going to, let's just say, rather than create flaps, let's just say that we're going to cut the corner pieces out and tape around the corners to make it a little easier to conceptualize, right? So then what are the dimensions of this volume going to be, of this open box, once I've cut it and folded it up? In terms of x, right? Because we don't yet know how deep to make the cuts. That's what we're going to control, right? We're going to control how much we're going to cut out of the corners. Agreed? And then we'll just fold the flaps up once we've made the cuts. So once we do that, in terms of x, which is our variable that we're going to be able to control, what are the dimensions of the box going to be? Okay, does everybody see that? Everybody see that? That if this whole thing is 9, then when we fold the ends up, it's going to be 9 minus 2x is going to be the new length, right? And if this was 5, when we fold the sides up, each one of those has a distance of x, right? Those are squares with side length x, and so it's going to be 5 minus 2x, and then the height of the box will be x, right? Everybody see that? So then if we add those up here, so this is 9 minus 2x, 5 minus 2x, and then the height right there is just going to be x. Okay, so what's the volume going to be? It's a polynomial. What would I do to get the volume? Just multiply them all together, right? And I don't even need to write it as a polynomial in standard form. It can just be a polynomial in factors form. That's fine because we're going to use graphing technology, right? So our volume function then, and this is what we'd call in calculus the primary function. It's the quantity that we're trying to minimize or maximize. In this case, maximize, right? The volume function is just going to be x times the quantity 9 minus 2x times the quantity 5 minus 2x, right? Everybody agree? Okay, so let's just go to Desmos and graph that and see what we get. Okay, so look what we get. Okay, let's go, I want to make how about change the scale just a little bit here. Let's let the x-axis go from -1 up to, I don't know, let's just say 6, huh? And the y-axis will go from -1 up to 20 maybe, and I'll say 25. Okay, how's that? All right, so there's our mathematical function, but we maybe need something else with this too, because we got to know where to look. So what's the domain going to be? What are the values of x that make sense? Because mathematically, if we look at this function, and this is a really important point. Everybody make sure you got total attention up here. Mathematically, are there any restrictions on this?
No.
There aren't, right? Because there's no place where I'd have to divide by 0. There's no place where I'd have to take an even root of a negative number. If I multiply it out, it's a polynomial. And what do we say about polynomials? What do mathematicians say about polynomials? Well, it's right, they're well behaved, right? Meaning they don't have any issues. Their domains are they're real every place. And there's some other calculus stuff that implies too. The derivatives, they're differentiable everywhere, but that's for a couple of years away. But the main thing for us now is the domains are unrestricted, okay? Mathematically, But this is a physical situation, so when we deal with an optimization problem like this, we have to say, okay, sure, we've got this mathematical function, but there might be some physical constraints or some geometrical constraints that supersede the mathematical domain, right? For example, would it make sense for x to be negative? Oh, is it time? Oh, I got you.
We're sitting here. Time's up.
Oh, that was the time? Oh, I got you. I thought it was a phone call. All right. Okay, so, all right, so
Yeah, she counts down.
I'm a minute away. Give me one more. Give me okay. So would you guys agree then, real quick, that x couldn't be negative, for example? That makes no physical sense. What's the biggest x could be before it couldn't even do it?
3.5.
No. Look at this. Look at this right here. If we've got 5 inches to deal with, what's the biggest I could make my cuts in the corners before they ran into each other? No, well, at what point would this thing not have any volume? If I just grow these squares, at some point they're going to bump into each other, and there's going to be no bottom to the box. 2.5, right? Does that make sense? So our domain, we really only have to go out to 2.5, and what do you know? If you look at our function here, oops, I lost it. See, look at that. From 0 to 2.5 is right there. Doesn't that make sense? Now hold it. You guys are eating into my time. Come on now. At 0, there would be no volume, right? Because the box has no height. At 2.5, there's no volume because the box has no base. There's the peak right there. Does Desmos give you a peak? I don't know if it does. We might have to do this on a graphing calculator. It does? If I just click right up there, it'll... Oh, there it is. Okay. So that's the maximum. Those are the dimensions when x is 1.032 and the maximum volume is 21.016. How about that? Go.
Yeah.
All right.
I thought we were doing Friday was all fun.
Oh, are you guys working or are we doing Friday?
Working.
Well, okay.
Boy. Are we doing the paper assignment or are we doing
The paper assignment, there's no Moodle assignment, so you're doing the paper assignment?
The only one we have.
Yeah. Yeah, for now. Say it again. Okay.